So I'm continuing the lecture from last class lecture. And so, I think there are some images that aren't showing or something weird is happening here. There we go. That makes more sense. So we were talking about where the density is in a pi bond and between the p orbitals. We're going to come to, so I got another question about resonance. We're going to be talking more about that in the day, in today and tomorrow and going forward. Yes, but the positive charge doesn't affect the overall stability of the molecule, but it affects, so Aaliyah asks, if all resonance structures of a molecule each have a positive charge, doesn't matter where it is. I mean, does its location affect its stability? Yes, it does. It affects the stability. The contribution that that particular resonance structure makes to the overall reality. So they're not all equal. Some resonance structures are more equal than others. They're better than others. And so ones where the positive charge is in a good spot makes sense. Now, if you have a positive charge on one structure in your resonance structures, all of your resonance structures have to have a positive charge, like an overall positive +1 charge, because you're not adding any electrons into the system. You have X number of electrons in every single resonance structure. And if that's positive, it's positive no matter what. What would be a good spot? Something with its full octet, ideally. If not, carbon. So we were just talking about the rules last class. Okay, so what I want to highlight here, and this is something that I see being made a mistake basically constantly whenever we evaluate this, is what is the pi bond? The pi bond, this is not a pi bond up here, this interaction at the top here. This is 1/2 of a pi bond. The second half of the pi bond is below. They are both together. They're the same thing. They're formed at the same time. They're separated in space, but they're one bond. That's a little confusing, I understand, but they are. I'm going to turn on my video because I talk with my hands. I have no idea if that's remotely helpful to anyone, but just in case it is. So, and then I'm going to minimize my window because I don't want it there. And then there's two of me, which is really confusing. Okay. So again, this pi bond is not cylindrically symmetric because it's on top and on the bottom, but it's on the sides. It doesn't go all the way around the molecule like a cylinder. It's kind of there's symmetry through the plane of the molecule, like cut right down through. I really can't draw it. I suck. But if you have a plane with all 4 of the hydrogens on it, and the 2 carbons, you're symmetrical right there. Okay. So far we've been talking very briefly about some, I'm going to call it MO theory. It's not really, but it's good enough for us. We've talked about these orbitals. We've talked about these orbitals interacting. We've seen p orbitals interact with p orbitals, and I told you that doesn't happen. We've seen s orbitals interact with s orbitals. Sorry, the p orbitals interact with p orbitals like this. They interact like this all the time, but like this doesn't happen. But we still have some problems because, well, when we look at methane, and we have it down here, methane's like perfectly symmetrical. It's got 4 carbon-hydrogen bonds. They're all 109.5 degrees from each other. Every single bond in that angle is 109.5, and they do that because that's a tetrahedron, and that's just the geometry of tetrahedra, and you're maximizing the distance between everything. That's as far as everything can be from everything else, and that's why it's that angle, because that is the angle that exists for tetrahedra. And all those bonds are the same length. But if we look at carbon, we've got the 1s orbital, we've got the 2s orbital, and we have the 2 p orbitals. And again, if we fill in all of its electrons as we should, ground state carbon, that's ground state carbon. It's got 6 electrons and 4 valence electrons. We have some problems. Like, you're trying to think, how is this thing going to make bonds? So the 2s orbital is full. It can't share an electron with another orbital. So right now, it looks like the 2s orbital can't make any bonds with another half-filled orbital. And we know that hydrogen It's going to use its 1s, and it's got a half-filled orbital. So there's no way that can interact with the 2s orbital, because that would give us a bonding and an anti-bonding orbital, but we'd have 3 electrons in there. So 2 would go into the bonding, 1 would go into the anti-bonding, that would be an unstable bond. So that's not good. Well, okay, we can sort of solve this problem by promoting an electron. So let's bump it up some energy. Let's put some energy into the system and say, okay, you're going to go up into the 2p. Okay, you had to put some energy into the system. The electron's not, the carbon's not in its ground state. It's not as happy as it wants to be. But I buy it. Sure. Okay, now we've got 4 orbitals. We got 4 bonds. That's awesome. But we've got another 2 problems. The first problem is I just told you all those bonds are the same length. And all of them are the same distance from each other, which tells you the energy of those bonds is the same. But the 2s orbital is not the same energy as the 2p orbitals. So that is a discrepancy. The other big discrepancy is we clearly have geometry. We got this tetrahedral geometry. And if I just look at what I got working with the 2s and 2p, my 2s orbital was a sphere. I don't know how to make a bond with a sphere because the sphere doesn't have directionality. So that's tough. And my 2p orbitals, well, they're going to be, one is in the plane of the page that way, one is in the plane of the page that way, and one is coming out towards me and going back and away. And I'm going to shade those in because those have different lobes, and I have learned my lesson, and I am going to use my mouse to pick a color. If my mouse responds. Okay, it's wiggling all over the place. So let's say we're going to shade the positive lobes green just because it was the first color I could pick. Now the problem there, of course, is we have these 3 mutually orthogonal, like perpendicular to each other bonds, but that's not tetrahedron shape. And they're equal in both ways. So would the hydrogen sit out in front of it, or would it sit out behind? And the hydrogens would all be 90 degrees to one another, and we're in trouble here. So this doesn't, you can't get there from there. So this is a problem. Okay, so we know why these angles appear because of, we're going to come back to that problem. We know why these angles appear because of valence shell electron pair repulsion. Electrons don't like being close to each other. They want to be as far away from each other as possible. So that's why you get the tetrahedron and methane, because everything can be as far away from each other as possible. So you want to maximize your angles. So an ethene, it's a stupid name. That's also a stupid name. Well, it's not as stupid. People still use that one. In ethene, and you'll know that's the En because you've practiced your nomenclature so far, hopefully. You've got a bond angle of about 120 degrees around that carbon-hydrogen bond. But of course, and I'm happy with 120. It's fine. I'm cool with that. Of course, it's not quite 120 because hydrogens are not the same thing as a carbon. So there's a few more electrons in this bond than there are in this bond. And so things want to be a little bit further away from this double bond than they want to be away from these single bonds. So you're kind of pushing these 2 single bonds a little bit together, and you're expanding those things out. And that still works. Ethine, of course, follows much simpler rules. There's 2 things attached to the carbon. There's a hydrogen and there's another carbon. And those guys want to get as far away from each other as possible. And since there's only 2, they can be opposite to each other and 180 degrees. We're still messed up on trying to figuring out the angles. And this is where we come into this idea of hybridization. So I'm going to go through this, and then we're going to discuss in a bit more detail. For some of you, you will have seen this. Some of you, I think, will never have seen this before. So what we're going to do is we're going to take your orbitals and we're going to throw them into a blender. So we're going to take a first look at ethine. And what we're looking at here is this carbon here. So what this carbon is doing is it's 2 times sigma bonds and 2 times a pi bond. Every multiple bond is a pi bond. If you have a double bond, that's 1 pi bond, 1 sigma bond. If you have a triple bond, it's 2 pi bonds, 1 sigma bond. Because the sigma bond's strongest, so whenever 2 atoms organic atoms come together and make a bond, they make a sigma bond first. But now you've occupied that space directly between the atoms. And so now any additional bonds are going to have to be interactions between p orbitals to make a pi bond, because you'll have that electron density above and below the atom, or in front and behind the atom, or I guess along either side, depending on your orientation. So if we think about carbon, again, we got 2s, we've got the 2 p's. We're going to need 2 p orbitals for that carbon. I'm going to do that whole electron promotion thing. Reserved for pi. So we're going to hold off 2 of those p orbitals. They're going to make a pi bond. And now I'm going to stick these 2 orbitals into a blender. It's going to be my little quantum blender. And what I'm going to come out of my blender is like a blender, everything comes out as a homogeneous mix. And they're called an sp orbital is what comes out. It's a mix between, each of those orbitals is 1/2 s, 1/2 p, which is confusing. But they have s nature and they have p nature. So you got 1 electron in each of these orbitals. Is there a relation between antibonding? Yes. So Mohammed asked, is there any nature or relation between bonding, antibonding, and hybridization? Yes and no. Hybridization is occurring before a bond is formed. Now that's not correct. Hybridization occurs as the bond is formed, and hybridization doesn't actually exist, and neither do orbitals. But because brain needs to be not broken, we're going to say hybridization occurs when a bond is formed. So as the atom is making a bond, it hybridizes as it needs to make that bond. Now it's making a bond, and its hybrid orbital is interacting with some other atom's hybrid orbital, and when those interact together, they make a bonding orbital and an antibonding orbital. But hybridization is a separate process, but it's concomitant, like it happens at exactly the same time that the bond is formed. Atoms are not hybridized if they are not making bonds. So you've got 2 sp hybrid orbitals that are formed out of this, because you get an sp and you get an sp. The overall density of the orbitals needs to be the same. And so we get 1 pointing one way and we get 1 pointing the other. And that's because that's not so much actually because of the shape of the original p orbitals going in. It's more because, again, we are maximizing the distance between the electrons in those orbitals. And note the shape is kind of like a p orbital. I'm going to draw sp orbitals like this, because that's wonderful that the textbook draws them like that. But I'm going to draw them like this. They've got a little nubbin at one end, and then they've got the bigger lobe. And it's because what we're going to be talking about is directionality here. These things are they're kind of like p orbitals, but with more direction. Okay. Where's my mouse? It is somewhere. What happened when I clicked that button? There we go. Okay. I have no idea where my mouse is. So The next set of orbitals on does hybridization happens between the orbitals on a single atom. Atoms hybridize individually, but they only hybridize when they interact with other atoms. But it's their orbitals that are hybridizing. sp orbitals are not the same energy as p orbitals. Sp, because you stuck a s and a p, you stuck them into the blender, total amount of energy needs to stay the same. So in an sp orbital, the energy is halfway between an s and a p. You put this much energy in from the s, and you got it from the p dropping down. And so the two sp orbitals are the same energy as each other, but they're higher in energy than s and are lower in energy than p. Okay, so is that because of the electron promotion? No, it's because this is the way that the atom can get geometries right, and it minimizes its energy. It's got nothing to do with the electron promotion. So sp2 orbitals, what we're going to do is we're going to take one s and two p's. And so this is, for example, in the example of ethene or tetramethyl. You know what? I'll put some hydrogens on there. We'll just say ethene. We're going to look at this guy. So this is a carbon. It's got one s. It's got three p's. Sorry, 2s, 2p. It's got one 2s orbital and three 2p orbitals. I'm conveniently just putting one electron in each orbital. That's not the ground state of this atom. I'm making bonds. I want one electron in each orbital. And we'll see why this is beneficial. We'll see why this is beneficial, and I'm just trying to figure out when I'm going to do that. Maybe, screw it, we'll do it today, if we have time. So this carbon here, it needs to reserve one of its p's to make the pi bond, because it's got 3 sigma, 1 pi. So it's got to reserve 1 p to make a pi bond. But it's going to take the other 3 orbitals, it's going to throw them into the blender. And so when it does the quantum blender, it comes out with 3 sp2 and 1 2p. Well, it's 3 times, I guess I should write this as 3 times 2 sp2, because they're in their second row resonance, or second orbitals. That's the word I'm looking for. Well, I don't know what else to say. I say resonance. So now these three sp2 orbitals are all equal in energy, and are all going to reorient themselves to get as far away from each other as possible. Now note that we put in one vertical and one horizontal, but our end result ends up with 3 in a plane, and the total vectors of those orbitals, the total electron density, the total shape of that is the same as what went in, but now they're distributed differently. We didn't have anything at an angle, but now we've got an orbital heading off at this angle, but that's because it took some of the horizontal nature of this guy and some of the vertical nature of this guy and was able to do that because that geometry was allowed. And they're maximizing their distance away from each other and are all 120 degrees. Now, what happens to that p orbital? Now, we were a little bit, didn't show this with the sp because it's just a little bit too messy, but it adopts the only space left to it, which is perpendicular to that plane formed by the 3 sp2s, because it can get as far away from those as possible. Now we have this geometry thing where you're going, well, why is it the p orbital that's perpendicular? Why isn't it one of the sp2s? And it's because the sp2s are lower in energy. The electrons are closer to the nucleus. So they're going to repel each other more than an electron in a p orbital, which is higher in energy and further away from the nucleus. So the sp2s are most concerned with being away from all the other sp2s. And then the electron in the p orbital is just kind of going, wee, I just trying to stay away from these guys, but, you know, get myself into the best position. But they're kind of ignoring me. So this is why you get this trigonal planar geometry in sp2 hybridized carbons. So all this molecule is flat. All atoms in the same plane. There are three. So there are three sp2s that are in the second level. They're all level 2, quantum number 2 orbitals. They're all in the second energy level. So they're made from 2s and 2p orbitals. So Casey asked why there are 3 times 2sp2. Nulia asked, Casey answered. There are 3 sp2 orbitals that come from 2s and 2p. I'm happy if you just call them sp2. You don't need to call them 2sp2. You just call them sp2. We know it's second row because that's what we're talking about in this course. I'll give that to you. But if we're going to be all formal, like, which I'm not good at, then they would be 3 times 2sp2. Abdul, I hope I answered your question because I didn't see it, and then I answered it. I think we're really looking that there are no atoms at the end of the p orbital, and so they're trying to. There's no shape there because there's no atoms at the end, and they kind of take over the leftover position once the sp2s have fought themselves into a draw. Okay, wonderful. Okay. That leaves us with sp3, where we're throwing in all the geometries. And now everything, we've got basically the 3 p orbitals between them basically cover up the entire sphere. And then you have this round s orbital. And so we have all the geometries. And the way these can best organize themselves is in a tetrahedron, because then everything is equidistant from everything else, and it's 109.5 degrees. And so in this case, this is something like methane. Okay, so I think this is the first time I've used wedge notation. This means out of the page. And the opposite with little lines going back into the page. How we got 3 sp2 orbitals. So going back, you know what, Abid, I think you might have just missed it and tuned out for a second. I'm just going to continue here. So what I've done here is I've used a line drawing formula. Well, I guess it's a Lewis line formula. I've drawn all the atoms, but I'm indicating 3-dimensionality. And that's because now suddenly we're reaching an atom that isn't flat. The sp and the sp2s were flat. The sp3 is not flat. It has 3-dimensionality. It's coming out of the plane for you. It's going in. It's doing things. That's the wrong spot. So what I want to take a look at here is, let's take a look at something we're just going to take a look at ethene in a bit more detail. And so there's a couple different ways we can look at this molecule. One way is we can use something called linear combination of atomic orbitals. Sorry, I inserted a blank slide here because I wanted to talk about this. What I'm doing there is I am going to linearly combine atomic orbitals. And so if I asked you to draw me the LCAO model of ethene, what I'm asking you to draw is basically, where are the orbitals? What are they doing? So let's think about what we have to do there. The first thing we need to do is we need to figure out, it won't last. Don't worry about that, Walter. The first thing we need to do is figure out what is the hybridization of every atom on here. Well, hydrogens are easy. They're all 1s. Because there's only one orbital, there's no hybridization. That's stupid easy. The carbon, what you need to do is you need to count the number of sigma bonds they need to make. And we'll discuss why in a second. Why we'll see a different example. There's multiple different ways this gets phrased. The most accurate way I think to phrase it is count the number of sigma bonds, because that tells us how many SPX bonds we're going to need. So this carbon is making 3 sigma bonds, 2 to hydrogen, 1 to carbon. So this must be sp2, because it needs 3 sigma bonds. One of those, and sp2 has 3 orbitals, because there's s1p2. We just don't write the little 1 because there's only ever one s. This carbon is likewise sp2 because it's symmetrical. Yeah. 3 sigma bonds equals sp2, 4 sigma bonds is sp3, 2 sigma bonds is sp, 1 sigma bond. That actually does exist. You can make a carbon with a 4 bond. I don't even know how that actually works. It's got to be just S. It's not hybridized. It's just really weird. So I'm counting the number of sigma bonds. And I'll count in purple. 1 sigma bond, 2 sigma bonds, 3 sigma bonds. There are 3 atoms attached to it, basically. And each atom is attached to a sigma bond. And then we have 1 pi bond. That's too much trouble to change color of the ink. So if I'm looking at the carbon, what I'm going to do is I know that the 2 carbons are held together by sp2 orbitals. And what do those look like? The standard of drawing I'm expecting from you guys is no higher than the standard of drawing I provide you guys. So I've got balloon animals connecting my 2 carbon atoms. There's going to be that other little lobe that goes with it, because the sp2 or spx orbitals all look the same. I'm not even going to try and differentiate between an sp and an sp3 orbital. They all look the same. The geometries are different, but they all look the same. Then I've got 2 sigma bonds going out to the hydrogens, which are 1s. So they're circles. Notice I'm deciding to draw, now it's fine if you wanted to draw the shaded ones in for all of these. I just think shading is hard, and so I prefer to minimize the shading. So everything is in phase. I've got non-shaded orbitals interacting with non-shaded orbitals, and those are bonding interactions, and that's all good, and the world is great. And they're little nubbins. By the time of the exam, I won't be asking for the nubbins, but anything else, anything you have to draw until then, you should put them in, just because you need to remember that they're there, that there is that other side to the lobe. It's not just unidirectional, there's also a backside, because we're going to be talking about that backside later. Now I am going to change color because this is the advantage, this is the advantage of having color. And that's, I need to draw the p orbital, and I am really sorry in advance. So what I'm drawing is the p orbital is coming out of the plane towards us and back into the plane away from us. It is perpendicular to the plane of my tablet. What are these things around to see? These are orbitals. I'm drawing the orbitals. These are all the orbitals. So in purple, p orbital, and in purple I have sp2 orbitals. The small things. The small things are the backside of the sp2 orbitals, because the sp2 orbitals have 2 lobes. They have a big lobe and they have a little lobe on the other side of the atom. And I am drawing in the little lobe on the other side of the atom. Yeah. So what I've drawn there is a linear combination of atomic orbitals. I'm going to indicate that there is a bond between the two p orbitals. I'm going to say that this is half a pi bond. If I'm now asking you to label all the bonds, this is half a pi. That's a sigma. 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 And I got the middle sigma. And so I've labeled all my atoms. I've labeled all my bonds. And I've indicated what these interactions are. And now I have this kind of orbital description of that simple line drawing I have up there. Now, another way I can describe this molecule is we can look at all the orbitals interacting one with another. So I'm going to create a new slide for that. And I will click through to the next slide, and it will stay clicked through to the next slide. It just, if I tell it that enough, maybe it'll actually do it. So I'm going to have this carbon and that carbon, and they have, so the hybrid that exists, they hybridize to make the bonds. And then we have hydrogen and hydrogen. I'm just going to draw in one of the hydrogens because of the way that energies work. I just, if I'm putting energy as a scale here, energy increases will go up the thing, and this is kind of like the x-axis is I don't know, it's like distance, I guess, sort of. I'm going to cheat by saying two hydrogens because there's two hydrogens on each of those. So each of those has an electron in it. Each of these orbitals has an electron in it. I'm actually going to just center this P over here, and you'll see why in a second. What I'm going to do is I'm going to show where the bonds are being made. So these two are interacting with 2 times this guy, and they're going to make a sigma and 2 times sigma star. Why can't p orbitals form a pi bond without the need to get hybridized with an s orbital? The p orbitals make a pi bond without being hybridized to an s orbital. That's what's happening. The pi bond is formed by p orbitals that aren't hybridized. But p orbitals can't join this way, and it's because of geometry restrictions. There's the s orbital in the way, and the s orbital needs to be involved. I don't really have a better way to explain. Well, maybe this will make a bit of sense where we're going with this. So this is for H1, this is for H2. And if we're, again, we just have the molecule sketched up here. There's no neat way to do this because I kind of only have like one axis. I almost need like a 3-dimensional electron coordination diagram, which is just insane and way beyond my drawing abilities. But, and I shouldn't have that as superscript. If I'm subscripting them, I'll subscript them. So we have 2 different H's on that side. We made 2 different sigma bonds. Note that this is beneficial, right? We took 4 electrons and we dropped their energy. They're now lower in energy because they're in a sigma bond. It's much lower in energy. Now, the one remaining sp2 is going to make a sigma bond with the other carbon. I'm going to draw it about the same level of energy. It's not, but who cares? I honestly mean who cares? I have no idea where it is relative to a CH bond. It's stronger, but I don't know how much stronger. So again, we take the two of the sp2 orbitals, electrons. We take the remaining sp2 orbital from the guy on the right, and we take an sp2 orbital from the guy on the left. They make a sigma bond. And then we're going to take the 2 p orbitals, and we're going to make a pi bond. And oh, look, the pi bond is weaker than the sigma bond. And I know it's weaker because it's higher in energy. The electrons in that pi bond are higher in energy than the electrons in the sigma bond, so they're easier, they're more energetic, they're more willing to not be in that bond and have things happen to them. And we have to create a pi star orbital. My distances are all supposed to be equal. It's just I suck at drawing. I want to change color. This is actually exactly the same description of the linear combination of atomic orbitals I just drew. It's just we're kind of looking at specific energies. Now we're looking at how the orbitals are interacting. We did it graphically earlier, and here we're kind of doing it, I don't know, mathematically, if that's the way you want to think about it. And then again, we've got two sigma bonds with the hydrogens over here. So this is H3 and H4. And then they have their corresponding sigma stars, which are empty. I'm never going to ask you to draw this. This is hard. For some of you, this will have made sense of that previous drawing. For others of you, it's like, please let me get back to the graph. I never want to draw this, ever, ever, ever. I don't care. Yes, you fill in the antibonding when there are electrons to fill it in. They're always there, but if you fill in the antibonding, they're antibonding. And so generally stable molecules do not have electrons in the antibonding orbital, because if they had electrons in their antibonding orbital, they wouldn't be stable molecules. So a lot of reactivity is going to occur because we're going to donate electrons to antibonding orbitals. Pi star will never be higher than, for a given sigma bond, sigma pi bond, pi star will never be higher in energy than a sigma star. Now, over the entire molecule, there might be some pi stars that are higher than some sigma stars in different places in the molecule. That is possible, especially when you have weird-ass elements involved. But when you have normal elements, pi star is always lower in energy than sigma star. Are molecular orbitals also stable in their half-filled? Sort of. That's my best answer. We'll get to some examples of that. So this is also a full orbital description of the molecule. To me, this is far less intuitive than that. I like this more. It's the same thing. It's exactly the same thing. It's just that you can draw very large molecules by stringing things together. This, if we got a lot more complicated than ethene, this would get insane very, very, very fast. So if we look at a few examples of these things, this is not an organic molecule because it doesn't have carbon in it. It's got beryllium, which is just weird. So beryllium, if you can remember where beryllium is, and I can't blame you if you can't, it's somewhere on the left-hand side of the periodic table, and I don't care. 180 degrees because it's BeH2. It's got 2 electrons on beryllium. Hydrogen's got 2 electrons. There's no lone pairs. It's what you get. It's like the purest form of an sp. There's no p orbitals on the beryllium. I'm being asked if I want to update my slide. We can go something that is actually a real molecule that is useful, which is borane. Borane, second row element. It has p orbitals. It's the element before carbon, right? What am I doing? So boron, 1s is filled, 2s is filled, and then 2p, it's got 1 electron. And so when you kind of spread the electrons out and start hybridizing to make bonds, because if you're making bonds, you are hybridizing, except for hydrogen and helium. And helium doesn't make bonds, so I guess it's not really relevant. Everybody else hybridizes when they make bonds. Now, In the case of boron, we've got an empty p orbital. That's fine, just 3 hydrogens. We're going to make 3 sigma bonds. We're going to throw these 3 orbitals into a blender, and we're going to get 3 sp2s. And then we're going to have this p orbital left over that was not tossed into the blender. It's still there, and it's empty. It's present. There's just nothing in it. There are no electrons in it. And then we've been talking a lot about things like methane, where we have the 3 sp3s. So again, if this is familiar to you, so the textbook I took this from was a European textbook. And so the Europeans and the North Americans disagree on how we should draw the back wedges. Now, you can normally tell from context which way it is. In North America, we tend to do that. We tend to start small at the space that is closer to you and get big as you get further away. So that means that hydrogen is behind that carbon on those red things. And then the big wedge is that hydrogen is towards me. The Europeans, of course, think, well, you should start small further away and then get bigger as you get closer together. They are, of course, right logically, but they are wrong because we're not European. I don't actually care which convention you use. Our textbook uses the North American convention, and my notes, I do need to update them, so I switched to a North American convention. You're Syrian. I have no idea what convention you use. Probably the French, to be honest. I don't know, do you use periods or commas when you're separating decimal points? The Middle East can get together and actually agree on something. Sorry. We're going to be sticking mostly to the North American convention. I'm going to be using the North American convention exclusively. And our textbook does too, and this slide is just from a British textbook. And if there's one thing that the British are teaching us right now, it is don't do what the British do. So what we're doing here, though, is we're drawing in 3D, and I'm indicating shape and I'm indicating directionality at this point. So here's just a little summary on this stuff. Sigma bonds and lone pairs. Actually, I wanted to get back to that example. Okay, so let's look at, because I haven't covered, do I have a spot? No, I don't. Okay, so here, this is the example I want to talk about. I'm going to talk about water. That's water. So what's its hybridization? Part of you wants to go, okay, I'm just going to count the sigma bonds, and I got 2. I got 2 things, and so it should be sp, but it's bent, so it's not sp. Lone pairs can occupy either hybrid orbitals or p orbitals, depending. Now, let's compare water if it adopts an sp conformation, or what makes sense, maybe an sp3 conformation. So here's our favorite friend, oxygen. Oxygen's got more electrons than carbon. sp oxygen. I'm going to try and draw everything in shape. So you'd have 2 orbitals midway between S and P, and 2 which are making bonds, and then 2 times p orbitals. So what we're going to do is just think about the total energy of this system, of the electrons in the system. We've got 2 electrons, and those have to be the lone ones because they're going to be making bonds. So you can't have 2 electrons in a bond-making orbital. So the lone pairs need to be in a p orbital. But that means you got 2 electrons in a very high energy orbital. That doesn't seem great. Whereas if it goes sp3, oops, what I drew there is not physically possible. It's lower in energy because we've lowered the energy of those 2 lone pairs down. And so the overall molecule is lower in energy. And so if we're making bonds, we're more stable if we can hybridize as much as possible because we drag down those lone pairs into a lower energy orbital. So water is sp3. So, but I want to put the caveat on here, and we'll get back to this next class. I think that this molecule, which is, ethanol, it doesn't exist. That's why I have trouble saying it. That oxygen there looks identical to the one I have up there. It looks bent and everything, but it's sp2. So I want to be cautious about what I say about lone pairs. Every sigma bond requires a hybridized orbital. Electrons will, whenever possible, the atom will hybridize to the lowest possible hybridization state. Like they'll go sp3 if they can. They'll go sp2 if they can't go sp3. And we'll talk about why that can't go sp3. Well, okay, no, the answer, I can answer that question of why this can't go sp3 just as the final thing in this class. And that's because we have a resonance structure. You might argue that this is a stupid resonance structure, and you would be right to argue that, but it is a valid resonance structure. And in that resonance structure, that oxygen is making a double bond. And if the oxygen is making a double bond, the oxygen needs a p orbital. And so it can't be sp3, because if it was sp3, it would not have any electrons in a p orbital. And then it wouldn't be able to make a double bond. And so there will be a benefit from being sp3, because all the electrons would be lower energy, but the benefit of being able to participate in resonance is more favorable than the benefit of being more hybridized. So the question that we got from Claire is, why are the electrons paired up on the second 2 sections of sp3 and not the first 2 for water? I think you mean up here, right? Claire? The one right below here. It completely arbitrary. It could have been, they're all the same energy. I could have stuck 2 lone pairs first or 2 after. Doesn't matter. It's entirely just, I don't know. It's just the way I do it. They're all the same energy, so I'll degenerate. Okay. I think we've just got to, I think we're done actually. These are the general rules. So sigma bonding and lone pairs under most circumstances occupy hybrid orbitals unless they can't, because you have to consider resonance. So that's why the first thing you should do is figure out what the hybridization is. And the first way to do that is figure out if there's any resonance. And we're going to have some examples of that coming up. They're going to adopt a geometry that gives the widest possible separation. And if there are multiple bonds between 2 atoms, you need pi bonds. And I think next class we're going to start talking about some pi bonds. But we'll move through this quite quickly because we kind of covered it today already. Okay. Thank you, everyone. I will talk to you starting next class, I guess. Have a really good day. I know the labs are challenging right now. We're trying to troubleshoot this. It's a learning experience for everyone. Everyone's going to go through the same first week, and we're going to try and learn some lessons from this, because we ran through all this with test students before this, test undergraduate students, and it went really, really smoothly. And of course, reality hits and it's not as smooth. So there are growing pains. We'll figure it out. Okay, take care, everyone. Bye. How do I stop recording? There we go.